Hello everyone, my name is Payam Aminpour. I'm a fourth-year PhD student at Michigan State University leading the work entitled Harnessing Local People's Collective Intelligence for Achieving Sustainable Ecosystems. Today, I will be presenting the results of two studies conducted through an interdisciplinary collaboration between Michigan State University, Northeastern University, and Unanimous AI Company with funding granted by NOVA. All right, let's get started with the definition of collective intelligence. To define collective intelligence, I want to use this beautiful wall painting from ancient Egyptian history showing a colossus on a sledge being transported by a group of workers. This painting is simply exemplifying a form of collective intelligence that uses the mechanism of division of labor, where the synchronized aggregation of fragmented efforts allows the optimization of work. In general, collective intelligence is a term we use to describe a group phenomenon that emerges from the interactions of various individuals or the aggregation of their independent problem-solving efforts such that the group ends up being more intelligent than any individuals alone, that is more efficient and more capable of solving problems and making decisions. Based on this definition, collective intelligence can be first thought to be a natural phenomenon common to many species like ants and fish. For example, a group of army ants foraging for food can collectively build complex structures or assemblages out of their bodies, such as a bridge to link disconnected places, and this is not achievable by any individual ants in isolation. Or a school of fish, while avoiding predators, can form a complex moving structure to become less vulnerable to predator attacks and increase the chance of survival. Collective intelligence is also a common phenomenon in human societies. Besides division of labor mechanism, human societies have long been practicing democracy to incorporate public opinions into important decisions and therefore thrive culturally and economically. Also, a group of people can take collective actions together to achieve a common objective like residents of a big city collectively practicing social distancing for slowing down the spread of coronavirus. Also, organizations can practice collaborative problem solving to make more informed decisions by integrating diverse knowledge and expertise and promoting innovations. By looking at these examples from nature and human societies, one question that comes to our mind is, when does a group outperform its individuals, or under what conditions a group's collective intelligence surpasses the individual's intelligence or problem-solving capabilities? This has long been a fundamental research question for researchers from different disciplines and has led many theoreticians to explain the underlying factors that make groups smarter and make them more effective in collective problem solving. For example, in the context of estimation and prediction, we can point out to the Francis Galton's observation in 1907, where a crowd of 800 farmers, butchers, and lay people were guessing the weight of an ox in a competition, and despite the fact that their individual estimates were mostly inaccurate with large errors, their average estimate was surprisingly close to the actual weight of the animal with less than 1% error. And this is what today is known as the wisdom of crowds effect. About 100 years later, James Surowiecki proposed four necessary conditions for leveraging the wisdom of crowds effect. According to the Surowiecki's the wisdom of crowds theory, crowd-based estimations can be very accurate when a large crowd of decentralized participants who represent diverse opinions make their judgments independent of each other, and their collective response is obtained through aggregating individual responses. And most of the time, it happens using the average. Dr. Scott Page from the University of Michigan offers a theoretical explanation for this phenomenon using a very simple mathematical model. Based on this model, the crowd error is equal to the average error minus the variance of individual errors. And because of that, higher diversity of responses may increase the variance of individual errors and therefore decrease the crowd error. And that's why Scott Page refers to it as the diversity theorem. Importantly, recent research shows that social influence and centralization can harm the wisdom of the crowd effect. In many cases, the social influence effect can diminish the diversity of responses without improvements of the average error, and because of that, collective error will increase. However, social interactions can also lead to another source of collective intelligence, which is known as swarm intelligence and is common among many non-human social species like ants, honeybees, and birds. In 2015, Dr. Louis Rosenberg proposed that once connected into real-time systems with decentralized and synchronous social interactions among individuals, human, humans can also amplify their group intelligence by forming human swarms. But since humans did not evolve the natural ability to form a swarm intelligence, they need to connect with each other with the aim of networking emerging technologies to form artificial swarm intelligence. So, emerging online technologies have provided humans with enormous potentials and unprecedented opportunities for generating new forms of collective intelligence to address our complex problems. But the important question here is, can we apply collective intelligence to address pressing and critical problems facing human societies today, such as unsustainable consumption of natural resources or unprecedented biodiversity loss? While human populations are growing, overexploitation of natural resources is becoming more common in human societies. In many places all around the globe, people consume natural resources intensively, degrade the ecosystems and natural habitats, and unfortunately, our information and knowledge about the status of these natural resources and their complex interactions with human societies are very limited. To address these limitations, we explored the use of online technologies to harness the collective intelligence of local stakeholders and natural resource users. Specifically, we use fisheries cases as examples of social ecological systems in which humans interact with natural resources. In the first case, which is already published in Frontiers in Ecology and the Environment, we looked at the striped bass recreational fisheries in Massachusetts, where we focused on using online technologies to harness the collective intelligence of recreational fishers for estimating fish abundance and demographics and approximating human pressures on fish resources. We reached out to three of the largest clubs for recreational striped bass fishing in Massachusetts. We first used an online survey to collect responses from a crowd of recreational fishers. We asked the crowd to estimate a striped bass population by size classes, estimate the number of recreational fishers in Massachusetts, to approximate fishing pressures, and estimate the most frequently and least frequently harvested fish size. Respondents independently participated in the online survey and provided their individual estimates. To aggregate the responses, we used the wisdom of the crowd approach. Individual responses were combined using the mean or the average for numeric items and the majority for multiple choice items. In addition, individuals participated in an online swarming experiment. Swarm is an online platform that allows users to interact in real time to collectively answer questions. The platform is synchronous, meaning that users can explore decision space together, and the software structures the social interactions among members. As you see in these videos, in our experiments, participants were able to answer questions by collectively moving a graphical park to select responses from among multiple choices, and a small graphical magnets on the screen pulling the park towards a specific choice show the individual's intents to select a specific answer. This figure shows the crowd average estimates versus the empirical data about percentage of fish population by size classes. For almost all size classes, crowd's estimate, which is the average of individual estimates, perfectly match the empirical data collected by NOVA, except for only one size class. In addition, this figure compares the crowd's and swarm's estimates of the number of licensed recreational fishermen in Massachusetts. As you can see in this figure, the crowd provided better estimation compared to the swarm of socially interacting individuals. The crowd estimate is only 5% off, while the swarm estimate is about 40% off. Still, both approaches outperformed a vast majority of individuals. These results also support previous findings about the negative impact of social influence on the collective accuracy in simple estimation tasks. However, both survey and swarm experiments produced accurate estimates of fish size for the most and least frequently harvested fish, yet again supporting the idea that by harnessing the collective intelligence of local fishing communities, we would be able to provide useful information about fisheries that we would otherwise achieve by costly investments in scientific assessments, massive data collection, and extensive monitoring systems. In the second case, we again used an example of striped bass fisheries in Massachusetts to explore the wisdom of the crowd's approach for pooling local knowledge about social ecological interdependencies. This paper has already been peer-reviewed and is under revision for resubmission to PNAS. In the traditional wisdom of the crowd approach, independent estimates of a large crowd of diverse individuals are aggregated using average-based techniques. But in our collective intelligence design, instead of numeric point estimates, here we aggregate the local knowledge of stakeholders about complex human fisheries interrelationships. In our experiment, participants used an online cognitive mapping technology called Mental Modeler and virtually created a digitalized model representing the individual knowledge about causal relationships between social and ecological components related to a striped bass population dynamics. Participants independently built their own cognitive maps using a highly decentralized environment with no influence from other participants and from researchers and facilitators. They were able to freely brainstorm, add their own list of concepts, and define causal relationships between them, all in an online graphical interface. A total of 32 individuals completed the task. The resulting graphical maps are called fuzzy cognitive maps, and we use them in our study to represent individuals' mental models and system knowledge about striped bass population dynamics and underlying social ecological relationships. Importantly, these fuzzy cognitive maps from a group of individuals can be mathematically aggregated using the average value of their edge weights or the magnitude of causal relationships to represent the collective knowledge of a group. We collected data from three stakeholder types: recreational fishers, commercial fishers, and fisheries managers. We first formed homogeneous pools of local knowledge by aggregating the maps of individuals from the same stakeholder type. And subsequently, we aggregated the maps across the stakeholder type to build the diverse pool of local knowledge. We compared the performance of these four aggregated models in two ways. First, we obtained subjective evaluations from a group of scientific experts who were actively involved in the scientific assessments and sustainable management of striped bass in Massachusetts. And second, we conducted an objective model evaluation using a stochastic network analysis to determine to what extent the system complexities were captured by each model. For the subjective evaluation, each expert participated in a semi-structured interview where they judged the performance of the four blinded models. Experts first rated these four models regarding the accuracy of causal connections and feedback loops. Box plots here show the normalized performance score given to each model by all experts. In overall, experts ranked the diverse crowd model higher compared to models of homogeneous groups regarding the structure of causal relationships in their maps. In addition, fuzzy cognitive maps are simulation models and can be used to predict system dynamic responses under different scenarios. As such, experts rated the models regarding the dynamic results they produce under 6 scenarios to evaluate the model's performance. The box plots here show the distribution of normalized scores given to each model by all experts. Again, the diverse crowd model overall has the highest score, showing its perfect performance in modeling system dynamics. In addition, we compared the aggregated models regarding how they represent system complexities. To that end, we examined their network micromotifs or microstructures that are constructed by 2 or 3 nodes and some unique patterns of connections between them. Prior theoretical and empirical studies have frequently suggested that 4 particular micromotifs represent more complex patterns of causality, and therefore their higher prevalence in a cognitive map may indicate higher perception and understanding of complex interdependencies. These are bidirectionality, multiple effects, indirect effect, and feedback loop. We used uniform random graph tests to measure the prevalence of each complex motifs in a cognitive map, and y-axis here show the deviation of motif counts from the expected values. As shown in this figure, among all models, the diverse crowd model demonstrated a prevalence above expectations for all complex motifs and thereby showing a more adequate representation of complex interdependencies. To conclude, we can state that accurate and reliable knowledge about complex human environment interactions can be generated from a group of non-scientist local stakeholders. However, a stakeholders' local knowledge needs to be aggregated through a collective intelligence design. In addition, when dealing with a complex task, knowledge diversity actually is a form of ability that improves the collective intelligence. And finally, these collective intelligence approaches have implications for many different natural resources and biodiversity conservation contexts, especially in data poor situations. Thank you so much. And if you have any questions or need a copy of the papers presented here, please ask us and we will try to get back to you as soon as possible. Hope you enjoyed this presentation and have a wonderful day.